Hi grade 12s and welcome to this video. In this video we will be working on the Mathematics grade 12 2022 term 1 control test. This is specifically from the Gauteng province and it is the Johannesburg North District paper. The test counts for a total of 100 marks and the time allocated is 2 hours. Okay, looking at the instructions, just make sure to round off to 2 decimal places unless stated otherwise. And remember that the diagrams are not necessarily drawn to scale. Okay, so with that being said, let's get into this video. Question 1, 1.1.1 says we need to solve x in this quadratic equation. Okay, so you can see that it has been put in standard form. So we can open up two brackets, equate to 0. Factors of x squared or x and x. Factors of 10, and that is, well, that could give us -7. So 5 and 2, and only the middle is negative. So they'll both be negative. So this is -5 minus 2. And so therefore x is equal to 5 or x is equal to +2. And those are answers. Moving on to the next question. The next question, we have another quadratic equation, but they say correct to 2 decimal places, so we know we have to use the quadratic formula, but it's not in its standard form yet, so let's just transpose that 10. So 3x squared plus 2x, and then what is +6 minus 10? That gives us -4 is equal to 0. Okay, so now we can see the value of a, the value of b, and the value of c in this quadratic equation. So here's our quadratic formula. So x is equal to negative and b is 2 plus minus the square root of b squared, which is 2 all squared, minus 4 times a, which is 3, and c, which is -4, all over 2a, and that is 3. Okay, so x is equal to, and let's just put this on the calculator, starting with the plus. Okay, so rounded off to 2 decimal places, we have 0 point, and that 8 rounds the 6 up to a 7. So 0.87, or x is equal to, and we can change that to a minus now, and we get -1.54. Okay, rounded up to 2 decimal places. And that is our answer. Moving on to the next question. Question 1.1.3, we have an equation. And we have x raised to the power of 1 over 2 plus 3 and then 1 over 4. You see what's going on here. Notice that it looks a lot like a quadratic equation. And that's because it is. You can make a quadratic. And you can make a quadratic by just spotting what is similar, okay, or what is really repeating itself. So you have an x to the power of 1 over 2. And you also have an x to the power of 1 over 4. But the thing about x to the power of 1 over 2 is that it can be written as x to the power of 1 over 4 raised to the power of 2. Okay, because those would multiply and then it becomes x to the power of 2 over 4, which is a half. Okay, so this x to the power of 1 over 2 is the squared version of x to the power of 1 over 4. So look at what we can do, and just to make this simpler, we can just go ahead and say, let k equal x to the power of 1 over 4. And so if k is equal to x to the power of 1 over 4, then that would mean that k squared, okay, if you square that, like squaring that, is x to the power of 1 over 2, okay, because 1 over 4 all squared, and then you see that those exponents multiply. 2 over 4 is 1 over 2. Okay, and let's go ahead and replace it. So in place of k to the power of 1 over 2, we just say k squared. So that's k squared, and we have plus 3, and there's 1 over 4, x to the power of 1 over 4, that is k. And minus 28 equals 0, and we have a quadratic equation. So open up two brackets, and we equate to 0. K multiplied by k gives us k squared, and then we need factors of -28. That can give us 3. We could try 7 times 4 is 28. Okay, so we know that 7, one of it needs to be negative. But because 3 is positive, make the smaller factor negative. So 7 minus 4 is 3. So we have positive 7, negative 4. So this means that k is equal to negative 7 or k equals positive 4. So we've solved for k, we still need to solve for x. So let's just go ahead and replace k back with x to the power of 4. So this is x to the power of 1 over 4, is equal to negative 7, or x to the power of 1 over 4 equals 4. And now we can finally find this. Now with equations like this, I try to be careful. Let's try to put it back in third form and see if it makes sense. So if we have x here and our radical, the inside exponent is 1, the outside exponent is 4. This is the fourth root of x, and we're saying that that is equal to negative 7. Consider whether that makes sense. You find the fourth root of something and it gives you negative 7, okay, or negative value. If you found the square root of a number and it gave you a negative value, this is impossible. You can't find the square root of a number and then it gives you a negative. Because if you said, for example, any number like 2 times 2 gives you positive 4. And if you say negative 2 times negative 2, it also gives you positive 4. So any number, okay, squared would always be positive, greater than 0. This also applies to fourth roots because you're multiplying a number 4 times. Okay, a number by itself 4 times. So it will become positive. It can't be negative. So this, I'm just going to go ahead and say there's no real solution here. And then that's what we have. X has no real solution. And then moving on to this one, if we had to rewrite this in third form, this is the fourth root of x is equal to 4. This is definitely possible. Okay, so we can go ahead and work on this. You can just find, you can put it in third form. That's fine. There's nothing wrong with that. And then to get rid of that fourth root, you can raise both sides to the power of 4. And therefore, this now becomes x because they cancel. And we have x is equal to 4 to the power of 4. Okay, that's 256. 256. And that is our answer. Okay, so that is our only valid solution. You can go ahead and test this out. If you had to, yeah, you shouldn't, but if you had to square both sides and solve for x here, you can take that solution and substitute it in place of x on your calculator and see whether it gives you 0. So this one would definitely not work. And then this one, if you try 256, it will definitely give you 0. So the left-hand side would be equal to the right-hand side. And so we've solved for this equation. Moving on to the next question. The next question, we have an equation with a surd. So first rule of these equations, isolate the surd. But you see that the surd is already on its own, so it's isolated, so we don't really have to do that. All we have to do is get rid of that root. So 2 minus x equals x minus 2, and let's go ahead and square both sides. So square, and now that cancels, and we have 2 minus x is equal to, and let's go ahead and square that. So I'll square the first term, that gives us x squared. Square the last term, that gives us positive 4. First term times second term is negative 2x times 2 is negative 4x. And then we have x squared minus 4x, and then when this comes over, it becomes a plus x, which will be negative 3x. And we have positive 4 here, and when this positive 2 comes over, it becomes minus 2, so that is positive 2. Okay, is equal to 0. And now we can go ahead and just say, open up two brackets, equate to 0, x times x gives us x squared, and then factors of 2 that can give us negative 3. So 2, because the middle is negative, you can just make both factors negative. So negative 2 minus 1 is negative 3, and negative 2 times negative 1 is positive 2. So this is minus 2 minus 1. Therefore, x is equal to 2, or x is equal to 1. Last step, make sure you check for the valid solution. So we're going to say the square root of, okay, because we tend to tamper with the solutions once you square both hand sides. Now we have a quadratic, but we didn't before. Okay, so this is 2 minus x, and it should be equal to the right hand side. So 2 minus, we'll try 2, the solution of 2. And then it should be equal to our right hand side, which is x minus 2. So 2 minus 2. And you can see that that is true. 2 minus 2, okay, square root of that is 0. And 2 minus 2 is also 0. So this works. Let's try 1. You can already see it's not going to work. 2 minus 1 is 1, square root of 1 is 1. But 1 minus 2 is negative 1. These are not the same numbers. So it means that x is not equal to 1, but it is equal to 2. And there we go. Make sure that you do show that you have cancelled that. You do get an extra mark for that. Okay, moving on to the next question. Question 1.2 says, given we have 3x squared plus kx minus 3x minus k is equal to 0, for which values of k will the equation have real roots? So just real roots in general. Let's go through what this means. We were given a quadratic equation, and they want us to find the values of k for which this equation has real roots. Where this comes from is you're trying to solve for x, the roots of your quadratic equation. Okay, and in a parabola, since this is a concave up parabola, since we can see 3, okay, is the coefficient of x squared, we're just trying to find those solutions, those x-intercepts. Those are our roots. Now, how we could also find them is using the quadratic formula, which looks like this. And you see that there is this part of the quadratic formula, b squared minus 4ac. This part we call the discriminant, and that tells you the nature of your roots. And the reason it tells you the nature of your roots is because it's the part that is square rooted. You see, if you square root a value, depending on what you square root, you can find out the kind of value you'll get. For example, if I square root a negative number, you'll get a non-real number. So automatically, your roots will be non-real. If I square a number that is greater than 0, okay, so anything greater than 0, then I'm going to get a root that is real. Okay, so this would be real. Now, there's also another condition that will make this real. If you square rooted 0, because the square root of 0 is just 0. So in that case, you would have negative b, whatever that number is, plus minus 0 over 2a. And so do you see here that in this case, if this is equal to 0, you would have just one solution because you're saying plus minus nothing, okay, plus minus 0. So your answer is really just negative b over 2a, which probably looks very familiar, okay? That is how we find the x value of the turning point in a parabola. And the reason we're getting this answer when we substitute 0 here is because if you had a parabola, right, and we're saying that this is equal to 0, the discriminant is equal to 0, and then you square root 0 to get 0. This is where we find when the discriminant is equal to 0, this is where we find equal roots. Meaning, for example, roots like x minus 1 times x minus 1, right? Those roots are equal roots, and they're really just one root, because what happens is in this equation, the reason it only has one root is because this parabola is actually sitting on the x-axis. Okay, so its intercept, its x-intercept is actually that turning point. And that is why when we make this equal to 0, we're actually finding the x value of the turning point, which is also the x-intercept now, the only x-intercept. Okay, that was just a rundown, and I only did that because this is a March paper. Okay, so just a little introduction to that. So in a nutshell, in order to find real roots, we just have to make that discriminant, okay? If it is anything that is greater than 0 or equal to 0, then it's going to be a real number. Whether the roots are equal or unequal, it will give you a real number. The only way it won't give you a real number is if that discriminant is a negative value, a value less than 0. Because if you square root a negative number, you get a non-real number. Okay, so that's what we need to focus on. Making the discriminant greater than or equal to 0. So delta is greater than or equal to 0, but we know that delta is b squared minus 4ac, so this is greater than or equal to 0. Let's figure out what a, b, and c are. So in this equation that we have, we can see that the value of a is 3, the value of b is interesting, but we can actually rewrite that a bit so that we can find the value of b. So here's the thing, you have 3x squared, and then notice that you have x here and you have x here. Why don't you just take x out as a common factor so you can see what is multiplying to x, and that would be the coefficient of x. So if we do that, what do we have in the first term? We have k, and in the second term, you have negative 3. So this is what we have, and then minus k equals 0. And so what this means is the value of A is 3. The value of B is actually k minus 3. And the value of C is negative k. And so we are saying B squared, which is k minus 3, and then we'll say all squared, minus 4 times A. So A is 3, as we can see, and then C is negative k. And we need to ensure that this is greater than or equal to 0. And this would solve for k for which the roots are real. Okay, so if you're looking for real roots, just make sure that delta is greater or equal to 0. Okay, let's go ahead and solve. So k all squared, that's k squared, and then the last term squared, positive 9. First term times second term is negative 3k, times 2 is negative 6k. Then these multiply, that becomes negative 12, that multiplies to give you positive 12k is greater than or equal to 0. And we have a quadratic equation. So this is k squared, that is 12k minus 6k is positive 6k, plus 9 is greater than or equal to 0. Okay, you can see that this is that one with the same roots. Okay, if you had to factorize this greater than or equal to 0, you see that we're going to have k times k, and then factors of 9 that can give us 6. That's positive 3 plus 3. Okay, 3 plus 3 is 6, but 3 times 3 is 9. So this is k plus 3 all squared is greater than or equal to 0. And then to solve for k here, now it can be tempting to just say, let's square root both hand sides. This is not an equation, okay? This is an inequality. And when you're looking for the values of k for which this expression is always going to be greater than or equal to 0, let's think about it algebraically first, and then we can look at a graph. So thinking about it, you're saying a value plus 3, and then you square it, and then it's greater than 0. Well, the minute you square it, it's always going to be either greater than or equal to 0. Okay, anything I put here, even if I put negative 8 plus 3, well, I'm going to square it. So at the end of the day, it doesn't matter that this gives me negative 5, because then I square it, and then it's a value greater than 0. So the lowest value that this expression can actually be is 0, because if k was equal to negative 3, and we said plus 3, and you squared that, then that would just give you 0, okay, because it's still 0. So here's a graphical explanation. You see, we have k plus 3 all squared is greater than 0. This is actually the case with equal roots. So here's what it looks like. If we draw a graph, the parabola is a concave parabola because we had k squared. Okay, so we have a parabola like this, and we have this parabola specifically not here, okay, but because we have this x-intercept really, okay, at negative 3. If you had to solve for x here, the critical value, if you're saying k plus 3 all squared equals 0, and you're finding the critical value, you'll find out that k is equal to negative 3. So this is what this parabola looks like. It has one intercept at negative 3. And the question is, for which values of k will this have y values or values that are always greater than or equal to 0? Well, its y value is equal to 0 here when k is equal to negative 3. And then where is it greater than 0? Values greater than 0 are here. Okay, so the graph will always have y values greater than 0. Can you see? For all values of k on this graph. This graph is never less than 0. Okay, it doesn't have any graph below here. So the answer to this for k is an element of all real numbers, and that is our answer. Moving on to the next question. Question 1.3, the last question for question 1 says, solve for x and y. Okay, so our first equation, we can see that it's linear. So we're going to go ahead and continue with this. So leave x on this left-hand side, and we still have 5 here. Then transpose the 3y, so minus 3y, and we can go ahead and call this equation 1. Then we can call this equation 2, and to solve for y, we're going to, since x is the subject here, we're going to substitute equation 1 into equation 2. Okay, so x squared, that's 5 minus 3y, so 5 minus 3y all squared plus, and we have y squared. So no brackets needed. So y squared is equal to 100 plus 5y. Okay, so let's solve for y. So square the first term, that gives us 25. Square the last term, that gives us positive 9y squared. First term times second term is negative 15y. Then times 2 is negative 30y. Okay, and then plus y squared. We might as well just transpose this because I can see these are going to become positive. So minus 5y minus 100 is equal to 0. So the y squareds, they add and become 10y squared. And then negative 30 minus 5, and that's only y, right? Yeah, so negative 35y. And then we have 25 as a constant. And okay, so that gives us negative 75. Okay, is equal to 0. You can see that these are divisible by 5. They can be divided by 5, so let's just divide both hand sides of the equation by 5, and we have 2y squared, and then that is negative 7y, okay, 35 divided by 5, and then here we have negative 15, okay, is equal to 0. And now we can factorize. So because we have 2y squared and it's not a common factor, I'm going to use the cross method. So we're going to take 2y squared and say what times what gives us 2y squared? That's 2y times y. And then factors of 15. So we need to space them out. 15 can be split into 3 and 5. But how do we put them? Okay, it's also negative. So one of those factors must be negative. So let's try 3 and 5. 3 and 5. I'm not sure it's going to work like this. That's going to be 10. And okay, yeah, that works out. So 1 needs to be negative. I'm just going to go ahead and make this negative because I can see it's going to become the bigger factor since the middle stayed negative. So you need the bigger factor to be negative, the smaller one to be positive, and that way your number will stay negative. So this stays positive. So if we multiply, we still need to check that this is valid. So 2y multiplied by negative 5 is negative 10y. And then y times 3 is positive 3y. And then this gives us negative 7y. So this works out. Great. And now we can finally write our factors down. So 2y plus 3y minus 5 equals 0. So 2y is equal to, you can just say 2y plus 3 equals 0. Or y minus 5 is equal to 0. And then solve for y here. 2y equals negative 3. Divide both hand sides of the equation by 2. Therefore, y equals negative 3 over 2. Or y equals 5. So we have solved for y, and now we can finally solve for x. And it's best to use equation 1 because it already had x as a subject. So 5 minus 3y is what we have. Okay, so this is x. So x is finally equal to 5 minus 3 times negative 3 over 2. And that becomes positive 9 over 2. So 5 plus 9 over 2, we can express this over 2 by putting it as 10 over 2, which is 5, yes. And then that is 19 over 2. Okay, so x equals 19 over 2, or the second solution for x is, we'll say 5 minus 3 multiplied by, and we'll substitute this y value of 5. So that becomes negative 15. 5 minus 15 is negative 10. So these are our answers. So x is either equal to 19 over 2, while y equals negative 3 over 2, or x is equal to negative 10, while y equals positive 5. Okay, and that is it for question 1, which is a total of 25 marks. Question 2, 2.1 says, consider the sequence, and we have 1, 4, 11, 22, and 37. So there's no clear consistency that we can see here that would suggest that this is a geometric or an arithmetic sequence. So it's probably a quadratic. Okay. And question 2.1.1 says, calculate the nth term. So let's see if we have a first difference. So we're going to say term 2 minus term 1. So this is 4 minus 1, which is 3. and then 11 minus 4, which is 7, 22 minus 11, which is 11, and then 37 minus 22, which is 15. And then let's see if we have a second constant difference. So 7 minus 3 is 4. And we also know that 11 minus 7 is also 4. 15 minus 11 is also 4. So this is a quadratic sequence. And we're going to take the first terms in the quadratic, the first difference and the second difference, and equate them to the following. So this is equal to 2a, this is equal to 3a plus b, and this is equal to a plus b plus c. Okay, let's go ahead and find a. So 2a equals 4. Divide both hand sides by 2, therefore a equals 2. And then 3a plus b equals 3, but we know that a is already 2, and plus b equals 3. So b is equal to, and that becomes 6. 3 minus 6 is negative 3. And then a plus b plus c, so this is 2 plus negative 3, which is minus 3, plus c equals 1. And c is equal to, we have 1 here. 2 minus 3 is negative 1. When you transpose it, it becomes positive, so c equals 2. So therefore, the nth term, okay, of this quadratic sequence is Tn equals 2n squared minus 3n plus 2. And that is our answer. Moving on to the next question. Question 2.1.2 says, which term in the sequence has a value of 407? So which term? So which term would mean term what has a value of this? So if they're saying term what, we can see this as Tn. Term what number has a value of 407. So in place of Tn, we substitute 407. And so we have 407 equals 2n squared minus 3n plus 2. Okay, and transpose. So 0 equals 2n squared minus 3n. And then if you say 2 minus 407, you get negative 405. Okay, there's clearly no common factor here, so we have to actually factorize. Okay, so open up 2 brackets equated to 0. If you're trying to save time, you can actually just use this method. So you can use the quadratic formula. Just make sure that you do find the factors. So here's how we can do this. So we're going to say negative b, and b is negative 3. So this is negative, and we have negative 3 plus minus the square root of b squared, which is negative 3, all squared minus 4ac. And then a is 2, and c is negative 405. And then over 2a. Now this would find the solution. Okay, so it's showing that one solution is 15, meaning n equals 15. And so if n is equal to 15, the factor that we must have had is n minus 15. Okay, because you said n minus 15 equals 0, and then, transposed it to solve for n. And then to find out what exactly that was, you can just change this plus to a minus to get the second root, and we get negative 27 over 2. So it means n is equal to negative 27 over 2. And what that means is that your factor was, you must have transposed that to get n plus 27 over 2. But then the 2 was in front of the n. So it was 2n plus 27. Okay, if you had 2n plus 27 and you said it was equal to 0, you see how you would have needed to transpose the 27 and then divide both hand sides by 2, leading to negative 27 over 2. Okay, so those are our factors, those are our answers. We can see which one is valid because we have a pattern. Patterns cannot have negative term numbers, okay? They can have negative term values, no problem. Okay, if this could be a negative value, that's fine. But it can't have negative term numbers. Because, for example, there's no such thing as the negative fifth position, okay? Because they are positions. So this is invalid also because it's a fraction. And then this is valid. So it means that term 15 is equal to 407. That is the term in the sequence which has a value of 407. So n is equal to 15 is your answer. Moving on to the next question. Question 2.2 says, how many terms are there in the following arithmetic sequence? So they told us it's arithmetic. It starts with 40. It ends with 202. Okay, so we know that it starts with term 1. And then we have term 2, term 3, term 4. And we're really just trying to find out what term does it end with. And that will tell us the amount of terms we have in this pattern. So find out this unknown term Tn. So it's very similar to this question. It's just an arithmetic sequence this time. So term what is this? And we can do that by using the general term of an arithmetic sequence, which is Tn equals a plus n minus 1 multiplied by d. Okay, so what is our difference here? The difference is 46 minus 40 is 6. So we have a constant difference of 6. So you can just show your values, okay? So we have this, yes, and a, the first term, is 40. D, the constant difference, is 6. And Tn, the value that it ends with, the last term, is 202. So substitute, we have 202 equals, and a is 40 plus n minus 1, and then multiply by 6. And we just have to solve for n. Okay, if we transpose 40, we have, and I'm just going to use a calculator for this quick. So 202 minus 40, and we have 162. So here on this side, we have 162 now, because we transpose the 40. And then here, you have 1 term times 2 terms. So this is 6 multiplied by n minus 1. Then we can just get rid of the 6 by dividing both hand sides of this equation by 6. And if you take this and you divide it by 6, not 2, 27. Okay, we get n minus 1 is equal to 27, and then transpose that 1. So n is finally equal to 28, and we can conclude there are 28 terms in this sequence. And that is our answer. And that is it for question 2. Question 3.1 says, the fourth term of an arithmetic sequence is -3, and the 20th term is -35. Determine the common difference and the first term. Okay, so they're giving you 2 pieces of information, and we have to use this. So they told us that the fourth term is -3, and term 20 is -35. These are term values of an arithmetic sequence. So simply use the general terms formula for an arithmetic sequence, which is Tn equals a plus n minus 1 multiplied by d. So here, let's input this information. So we have term 4 equals, we don't know what the first term is, so we leave it as a, plus n is 4, because we're saying term 4 in place of n. So 4 minus 1 multiplied by, and we also don't know what d is. We're trying to find that. Okay, so term 4 is equal to -3, which is a, and this becomes plus, this is 3 times d, which is 3d. Okay, and then the second piece of information they gave us was term 20. So term 20 equals a plus 20 minus 1 multiplied by d, and then that becomes -35 is equal to a plus, and that is 19d. Okay, so these are 2 equations. You can solve them whichever method you want, okay, elimination method or making one thing the subject. Here, I'll just make a the subject in both equations. So if we leave a on the right-hand side, we're going to transpose the 3d. So this becomes -3 minus 3d, and then a equals, and this is -35 minus 19d. And finally, we can say that a is equal to a. Therefore, -3d, I mean, you could just make them both positive, but it's fine. Okay, -3 minus 3d equals -35 minus 19d. And then if you transpose it, this becomes positive. So 19d minus 3d is equal to, and we have, this will become +3 minus 35. And so here we have 16d is equal to, and this becomes -32, and divide both hand sides by 16. And we finally find out that d is equal to -2, okay, because that's double of it. And now we can find a. So we found d. To find a, just take this value of d and substitute it into either one of these equations. So a is equal to, and we can say -3 minus 3 D, which is negative 2. And so A is equal to, that becomes positive 6. 6 minus 3 is 3. And there we go. A equals 3, while D equals negative 2. Moving on to the next question. Question 3.2, they tell us to evaluate the sum. So they express it in sigma notation. Sigma just means sum. So just add the sequence starting at k equals 1 and then add k equals 20 with this formula, okay, or this general form. Okay, straight away you see that the k, the unknown value, is in the exponent. So this is a geometric sequence. And you can expand it, but it's not really necessary. Just focus on getting the things that you need. First, we need, so let's just put down our formula. We have two formulas for the sum of series in a geometric series. Here's the first one. And we use this when r is greater than 1, which we can see here. Okay, the value of r is whatever is carrying the positive exponent, okay, of that variable. So we can see it's 3 to the power of k. That's what we have there. It's not like this is negative. If it was negative, then you need to think it through, because what could happen is that you could have a 3 raised to the power of negative k. That doesn't mean that your ratio is 3. Okay, this is a negative k, so you can't even see what it is yet. You have to first take out that exponent of negative 1, and then it's still being multiplied by the k. Now 3 to the power of negative 1 is actually 1 over 3. Okay, so in this case, the ratio would actually be 1 over 3. So just be careful. As long as you see it's raised to a positive, okay, exponent of that variable k or n, then you know that, okay, that base is your ratio. Okay, so we can see that r is greater than 1, so we don't have to use the other one that says 1 minus r raised to the power of n. Okay, so with this, we can see that a, well, we need to find a, but we can see that r is equal to 3. And to find a is the first term. They said k starts at 1. So if k starts at 1, you're just going to substitute 1 in place of k there. So we have 3 to the power of 1 minus 2. 1 minus 2 is negative 1. 3 to the power of negative 1 is 1 over 3. Okay, so let's just substitute and find our value. Okay, there's one more thing we need to find. You need to find the number of terms you have, because you're trying to find the sum of your series. And we'll find that by saying top minus bottom plus 1. You see, in this case, there's no confusion because we started at k equals 1. So it's perfectly fine. It actually is 20. So we'll say the sum of 20 terms is equal to, and a is 1 over 3 multiplied by r is 3 raised to the power of 20, and then minus 1 all over r minus 1, which is 3 minus 1. And let's just find the sum of these 20 terms. And we have, okay, this is 1, 2, 3, 1, 2, 3, so 581,130,733 point, and now you see that is like 3 recurring. So we can just round off to 2 decimal places since that's what the instructions usually say, okay, unless stated otherwise. So 0.33, and that is our answer. Moving on to the next question. Question 3.3 says, the following sequence forms a convergent geometric sequence. Remember what it means for a sequence or a geometric sequence to converge. It means that the ratio is a value greater than negative 1 but less than 1. But of course, for this sequence to exist, okay, with these parameters, then r should not be equal to 0, because you can't have a ratio of 0. Okay, if you have a number, then you say, okay, my constant ratio is 0 times 0. Well, that's going to give you 0. And then times 0, that's going to give you 0. And so that doesn't even make sense. How did you find r if r was equal to 0? Because then you're going to have an undefined value when even trying to find r. Okay, so just keep that in mind as well. So they say we need to determine the possible values of x. So this is for which the series would converge. So let's see. This is our first term, second term, clearly third term. So let's just find r. Since we know it's a convergent geometric sequence, we can just find, it's a series really, we can just find r. And to find r, just always take the next term divided by the previous term. Okay, you can also say this term divided by this term. So yeah, I like to take the easiest one that we can take. let's try 1 over 3 divided by 1 over x minus 1. And then because we're dividing, we can use tip and times. So you tip this, swap the numerator and denominator, change the division to multiplication. And so r is just x minus 1 over 3. Okay, so this is the value of r, and now we can finally just find out the values of x for which the series converges. So for the series to converge, r is greater than 1, is greater than negative 1. So this is x minus 1 over 3 is greater than negative 1 but less than 1, but it shouldn't be equal to 0. So let's just find out what that should be. If the ratio r minus 1 over 3 shouldn't be equal to 0, what should x be for this to happen? You can cross multiply, it's fine. Or multiply both hand sides by 3. So if you times 3 here, times 3 here, this 3 cancels. And then you have x minus 1 is equal to 0. And then, or is not equal to 0. And then transpose it. So x should not be equal to 1. Okay, I'll keep that in mind. And now let's finally solve for this inequality. Okay. We have 3 in the denominator, just multiply all sides by 3. Then you have x minus 1, and if you multiply by 3, it cancels the 3 here. It multiplies here and becomes negative 3, multiplies here and becomes 3. And now this is what we have. Then transpose the negative 1. So take it over on both sides because these are actually two inequalities that have been written together. So when it comes over, it becomes positive 1 here. Negative 3 plus 1 is negative 2. And when it becomes positive 1 here, that becomes 4. And so what we have is that x is greater than negative 2, but less than 4. But x should not be equal to 1. Okay, because you can see that 1 is a value between that. And that is our answer. Okay, moving on to the next question. Question 3.3.2 says, if x is equal to 2, calculate the sum to infinity. Okay, so to find the sum to infinity, remember that. Let's just remember what that formula is. Sum to infinity equals a over 1 minus r. So we just need two things. We need the value of a, the first term, and the constant ratio r. So we have r, it's x minus 1 over 3. So let's just put that down. So r is equal to x minus 1 over 3. Since x is equal to 2, this is 2 minus 1 over 3. So 2 minus 1 is 1 and r is equal to a third. Okay, makes sense. That's why it converges. And then we need to find a. So a, this first term, is 3 over x minus 1 all squared. Okay, so let's find a. A is 3 over x minus 1 all squared. But we know now that x is 2. Okay, so 2. And so 2 minus 1 is 1. 1 squared is the 1. So a is equal to 3. Okay, so the sum to infinity would be sum to infinity is equal to a, which is 3 over 1 minus, and then r is 1 over 3. So we can just find this. This is 3 divided by 2 over 3, which we can just say is 3 multiplied by 3 over 2. And so you see that's just going to be 9 over 2. Okay, so this is equal to 9 over 2. And that is our answer. Okay, and that is it for question 3. Question 4.1 says, given sine 24 degrees is equal to m and cos 35 degrees is equal to n, so these look like trig diagrams, determine the following in terms of m or n. Okay, so since they're both, diagrams, let's just draw them out. So we have sine 24 degrees is equal to m, and then we have cos 35 degrees is equal to n. And let's draw our diagrams. So they will both be in the first quadrant. And the reason why is because 24 degrees, if you measure, that is in the first quadrant. Greater than 0 degrees, but less than 90 degrees. So we could just measure that there and say this is our angle 24 degrees, and then a line down to the x-axis, perpendicular. Okay, so this is sine 24 degrees is equal to m. Now, sine, remember from SOHCAHTOA, sine is opposite over hypotenuse. So if this is opposite over hypotenuse, m is the opposite side, and then the hypotenuse is this natural denominator of 1, which is 1. Okay, so all we have to find here, would be the adjacent side. And then we can also draw the second diagram. The second diagram is with 35 degrees and it looks like that. So we'll just measure 35 degrees. And then you know that cos from SOHCAHTOA is adjacent over hypotenuse. So the adjacent side, just draw a line down perpendicular to the x-axis. And so because it is adjacent over hypotenuse, this is the adjacent side. And then the hypotenuse is also 1. Okay, so this is 1 and we have an adjacent side of n. Okay, so in both, let's just find this. We already know you can just go ahead and find it like step by step, but naturally this will be 1 minus m squared. Okay, I'll just show you how we find it. So this is the adjacent side, we can call it x. So x squared is equal to, and you take the hypotenuse squared minus the opposite side squared, and then we square root both hand sides. Okay, consider the positive or negative, but remember that this is in the first quadrant where the x value here is positive. So we're saying x is equal to the square root of 1 minus m squared. Same thing over here to find this, which is a y value. Okay, so that y squared equals hypotenuse squared minus n squared. And then square root both hand sides. And then y is also positive, okay? It's equal to the square root of 1 minus n squared. Okay, so this, we know both of them. Okay, and we can just put them down and then just find those values. So this is the square root of 1 minus m squared, and that is the square root of 1 minus n squared. And now let's just find these that they asked us to find. So 4.1.1 asks for tan 66 degrees. Okay, so let's find the value of tan 66 degrees. Tan 66 degrees will be found by focusing on 66. And remember that tan from SOHCAHTOA is TOA, so opposite over adjacent. So we're looking at 66 degrees. And which side is opposite this angle? The side opposite this angle would be this square root of 1 minus m squared. And then the side next to this angle is the m. So we'll know that this is simply equal to the square root of 1 minus m squared over m. And that is our answer over there. And then, of course, 4.1.2, they specifically asked for sine 70 degrees. Now, you can see that 70 degrees, it's double of 35 degrees, meaning we could have just rewritten this as sine 2 multiplied by 35 degrees. And so this is using double angles. So we could just use the double angle identity for sine 2a, which is 2 sine a, so sine 35 degrees, cos 35 degrees. Okay, so they are multiplying. Let's go ahead and find this. So this is 2 multiplied by, what is sine 35 degrees in this diagram? Okay, so that is the opposite over hypotenuse. So that is the square root of 1 minus n squared over 1, but you know anything over 1 will just stay the same. And then multiply by cos 35 degrees. And cos is adjacent over hypotenuse. So that is n over 1, and so that is multiplied by n. And so this is simply just 2n square root 1 minus n squared. And that is our answer over there. So these are our answers. Moving on to the next question. Question 4.2 says, prove that sine 45 degrees plus x multiplied by sine 45 degrees minus x is equal to cos 2x over 2. Okay, now it could be a case where we could simplify this further, but right now we can see that the left-hand side is what we can actually work with. We can actually expand this. So let's go ahead and say that the left-hand side is equal to, and rewrite. So this is equal to, we can expand both. So this is going to be sine 45 degrees cos x. Okay, so this is using the identity for sine a plus b. And you can see this one is sine a minus b. Okay, so sine 45 degrees cos x plus cos 45 degrees sine x. Okay, and it's multiplying. So these two are multiplying. So we'll say multiplied by, and then let's put the second one. So the second one is with the minus. So we have sine 45 degrees, and then cos x, and then that just changes to a minus, and then cos 45 degrees sine x. Okay, so these two are multiplying, and yeah, do you see how this and this is exactly the same, and this is also exactly the same, and then we have a plus and a minus. So this is difference of two squares. Just like we had x minus 2 and then x plus 2, you see how that's the same, and then plus minus. We can simplify it too. So we're going to multiply the two first terms. And so that becomes sine squared 45 degrees cos squared x. And then the two last terms, but we put a minus in the middle. So that becomes cos squared 45 degrees times sine squared x. Okay. And then this is equal to, these can be written as numbers. Now, you can choose to use any diagram that you want. You can use the calculator. In this case, it wouldn't matter because you're still squaring this number at the end of the day. So it's still going to simplify to a simplified fraction. So it doesn't matter, okay? But I'm going to go ahead and say it's equal to 1 over root 2 instead of root 2 over 2. Okay, on the calculator, you would get this. But don't worry, it doesn't really matter in this case. You're still squaring it. So that is squared because we had sine squared 45 degrees. And then this is multiplied by cos squared x. And then minus, and then cos squared 45 degrees, cos 45 degrees would also be equal to 1 over square root 2, or square root 2 over 2. And that gets squared. Multiplied by sine squared x. Okay, so let's see. Okay, so straight away I can already see it's following the cos squared x minus sine squared x. Okay, so yeah, that's definitely where they got the cos 2x. So this is equal to, they get squared, the 1 gets squared and becomes 1, the root 2 gets squared and becomes 2, and you have a half cos squared x. And then same thing happens there, it's minus 1 over 2 sine squared x. And we have a half common, so we take a half out as a common factor, and we have cos squared x minus sine squared x. And then this is the identity for, say, cos squared x minus sine squared x. It is equal to cos 2x. So this is actually a half multiplied by cos 2x. And let's see what the right-hand side was. Okay, so they just put it over 2, meaning here the numerators 1 and cos 2x multiply, and they just become cos 2x. And then the denominators 2 and this invisible denominator of 1 multiply, and they become 2. So there we go. It's equal to the right-hand side. And we have proven that identity. Moving on to the next question. Question 4.3, we've been given cos x plus 42 degrees is equal to sine 2x, and we need to solve for x if x is an element of negative 180 degrees all the way to 180 degrees. So this is like general solution, but once you find the general solution, you're going to look for specific solutions within this interval. Okay, so we're working with it as if we are finding the general solution. So this is equal to sine 2x. Straight away, what do you notice? One has x, the other has 2x. You can't just work with them like that. You can't even form tan x like this. So what would be advisable to do is to change one of these to cos or sine. So you can change this to sine, or you could change this to cos. And I'd rather go with changing this to cos, okay? So they will both have cos, and we'll be able to use the second function of cos. So x plus 42 degrees is equal to, and we'll change this to cos 90 degrees minus 2x. Okay, so now they're both cos and cos. And now we can find the reference angle. I'll leave this on this side. So this is what is going to be the subject of our equation. And so I'm saying this is the reference angle we're finding. And you find that reference angle, it's like taking cos over. When it comes over, it becomes the second function of cos. And so if you apply the second function of cos here, because it is the inverse of this. This is cos of this. This is the second function of cos. They're the inverse of each other. They would cancel. Okay, so that is gone. And now what we would have is whatever was inside. Okay, so our reference angle is currently 90 degrees minus 2x. And now we can finally solve for x. Okay, so you can consider the cos diagram and just consider where cos is positive or where it's not negative. Okay, when we have the scenario like that, you don't have to overthink it. So this would be in the first and the fourth quadrant. And the reductions there on theta, and then we have 360 degrees minus theta. So we're going to say what is our subject, okay, is whatever you left here when we were applying the second function of cos, when we took that over. So that's what we're trying to solve for. We will have x plus 42 degrees is equal to, and we first have theta, so we'll leave whatever our reference angle is, which is 90 degrees minus 2x. So 90 degrees minus 2x. Then you need to say plus k of, and this is cos, we're using cos, so the cos graph repeats itself every 360 degrees. It takes 360 degrees to complete one cycle. So this is plus k 360 degrees, or second solution, we say x plus 42 degrees is equal to 360 degrees minus theta, and our theta here, our reference angle, is 90 degrees minus 2x. I'm just going to go ahead and subtract by both values we have here. So minus 90 degrees will be negative 90 degrees, minus negative 2x will become positive 2x. And then again, plus k of 360 degrees, where k is an element of integers. Make sure that you write this at least once, okay? You just need it once there, so they know what k is. You've defined k. And now we're just finding the answers. Then we'll find it within that interval they gave us. So we have over here, we can just transpose this to x. So it comes over and adds with this x to become 3x is equal to, and then we have 90 and the 40 degrees, 42 degrees comes over. 90 minus 40 is 50, and then minus 2 is 48. So we have 48 degrees here plus k 360 degrees. And then to solve for x, we can divide both hand sides of the equation by 3. Okay, so x is equal to 48 divided by 3, 16. Yes, okay. 16 plus k 120 degrees. So this is our answer here. Okay, then second solution, or here, let's just simplify. So we have, well, we can transpose that. It's just going to be x and then minus 2x, which gives us a negative x. Here, when you subtract 360 and 90, you get 270, and then minus 42 degrees. That's, we still have the 200, and then 30 minus 2 is 28. Okay, so that's going to be 228 degrees. Okay, now if the answer, because in this situation, when we're solving for cos, for example, if we said cos theta when we're using the function cos, right, is equal to, for example, let's just say root 3 over 2, right? Then once you find your reference angle, here, this is going to be 30 degrees. There's two ways you could have solved for this. You could have either said theta was equal to 30 degrees, okay, using the first and fourth quadrant, right? Theta equals 30 degrees, and then plus k 360 degrees, or theta equals 360 degrees minus 30 degrees. Okay, and that's the method we just used, the table method, which is used a lot by most schools and stuff. So I just decided to use this method. But there's another method. You could have used this method where you say to find theta, you simply say that it's equal to positive or negative reference angle, okay, 30 degrees. And so on one hand, you would have theta equals 30 degrees. On the other, you would have theta equals negative 30 degrees. But it's still the same thing, okay? Because here the angle is just negative. If you made the angle positive, because the cos graph repeats itself every 360 degrees, and it really just depends on whatever you have here. If you're still left with k 360 degrees, and you still see the 360, then to get the positive angle, you add 360 degrees. Okay, if you added 360 degrees to this, you see how it's still going to be 360 minus 30, which is also 330 degrees. Okay, so if you do see another angle there and it's negative, just add whatever angle that you have here. Okay, whatever this, however long it takes for the cos graph to repeat, and then you're going to see that it would still be this answer. Okay, so we have 228 degrees and then plus k 360 degrees. Then divide both hand sides by -1 or multiply by -1. And finally here we're saying that x is equal to -228 degrees and then minus k, 360 degrees. Okay, so this is our answer. Now, our answers will still be exactly the same, regardless of the method that you use, because we're specifically trying to find the solutions between negative 180, so from negative 180 all the way to 180 degrees. And let's go ahead and find that. Okay, let's go ahead and find these. So let's start with 16 degrees. I'm going to just put a number line so I can accept numbers and the ones I don't accept. Remember how k is an element of integers? So that means that in place of k, we're going to put integer values. So that's k and then times 120 degrees. Okay, so integer values, let's start with 0. If you put 0 there, you see that you get 16 degrees, which is an acceptable answer. If we try 1, we get 136 degrees. And let me actually just put this restriction here so that we can just keep track of it. Okay, so when we use 1, where k equals 1, this integer values, okay, we have 136 degrees, which is acceptable as well. When you try k equals 2, you get 256, which you can see is above your domain, okay? This is, we have to take values that are equal to 180 or less. So that doesn't work, and so you don't need to try the integer value 3. And then let's try negative 1. So if we try minus 1, we get negative 104 degrees. That is acceptable, okay? It's within this. And then let's try negative 2. We get negative 224 degrees, which you can see does not work, and you don't have to try that. So these are the answers that we get here, okay? And then we're going to do the same thing for this solution. So let's rewrite that on a calculator. So let's try 1. Okay, again, I'll use a number line here. It's just easier to keep track of it. Let's try 0 first. So if you try 0, you get negative 228 degrees. That is not within the restriction they asked for. Okay, it's not within these boundaries. So we'll leave that. That doesn't work. So what happens if we try 1? Then we get negative 588 degrees, which is too far. Okay, too far beyond. It's too small. So we can't accept that. That doesn't work. Let's try negative 1. We get 132 degrees, which is really a repeated solution that we have. 132 degrees, okay? And then if you try 2, you see that that's already beyond it, okay? Negative 2 doesn't work. Okay, so from this, oh, it's not actually a repeated solution. So from this, these are our answers. Okay, so you can see that we have about 4 solutions. So there's no use of writing it as x equals then this and then that and that. So we can just say x is an element of, and let's put down all our answers, okay, between the braces. So first solution, the smallest one is negative 104 degrees, followed by 16 degrees, and then 132 degrees, and then lastly 136 degrees. And these are our 4 solutions. As long as you get these solutions, whichever method you use is fine. And that is it for question 4. Question 5 says a mountain climber wants to determine the height PQ. Okay, that height. And this is the height of a mountain. The climber is standing at R. Okay, so this is where the climber is standing at R. And they also say on a flat ground. Okay. R and S are in the same horizontal plane as the foot of the mountain. So these 3 points are on the ground. Okay, so you see, this climber can walk to this point. It's not walking down a mountain, it's walking on a flat ground. Okay, then from R, he measures the following angles. The angle of elevation of the top of the mountain, P, is W. Okay, so the angle of elevation there, and then PRS, angle PRS, this angle is X. He then walks Z meters to point S, okay, and measures RSP, this angle, which is Y. Okay, so they're just explaining all the sides and angles we have. So the first question says, show that PQ is equal to, Z sine Y sine W and then sine X plus Y. So let's try not to stress too much about this part because there's just a lot of hints here. Okay, so we'll just try to follow what they were doing, but also keeping in mind that we're trying to find PQ. How would we find PQ? Okay, so to find PQ, I'm already just, because this part is already looking very intimidating, so let's just look at that quick. X plus y. Why would we ever need to add angle X and angle Y? Okay, clearly if you were using this triangle and you were trying to, for some reason, find this angle. So it has something to do with this angle. Why would we be trying to find this angle, and how does it relate to finding PQ? Well, it says sine x plus y. We know this is going to be, it's not x plus y, but it's going to be 180 degrees minus x and then minus y. So if you added these together, you could have said to find this angle, you say 180 degrees because the angles in a triangle add up to 180 degrees. And then you say minus, if you take x and y together and you subtract them by 180 degrees, you will get that angle. Okay, and then the fact that they have sine there clearly means that they use the sine rule. Okay, so to use the sine rule with this angle, you must use this side. Makes sense now? That's why z is there. Okay, and then we need to pair it with another side. Which side did they pair it with? Well, I don't see any sine x alone. If there was a sine x, I would say, oh, they paired it with ps. But clearly there isn't. So they must have said sine y, and then you have to take the side opposite angle y, which is PR. Okay, so this makes sense. It's a story. It's like they just moved from this triangle, and they started with this triangle, and they clearly found PR. Okay, so you see, if we try to find PQ, we could find PQ by using this angle here, because this is the right angle triangle that we have. We could simply use this angle and say it's opposite over hypotenuse. Clearly they use sine, okay, because there's sine going on all over here. But mostly because they have sine W, okay, that's the reason why. So sine W would have given us, so here's the thing. We are just going to say sine W is equal to, and would say, opposite over hypotenuse. Well, let's start off there. Sine W equals, the opposite side is PQ over the hypotenuse, which is PR. And then you see that they went through this whole thing of finding PR. Okay, but since PQ was the subject here, they clearly made PQ the subject. So we're going to leave PQ here. And you see that to do that, you need to get rid of PR. And you can do that by multiplying both hand sides by PR. Okay, so this is what we have. So we have, and I'm going to leave PQ here, is equal to, and that is PR multiplied by sine W. Okay, and now we can focus on finding PR. Okay, how do we find PR? So you could see with the whole explanation in the beginning, they clearly use the sine rule. So we're going to take this side and then the angle opposite it. Okay, so that is PR over sine y. So say PR over sine y is equal to, and you need to take another side and angle that is complete. So that would be the z and then this angle. Okay, that was that x plus y that they got. So yeah, we clearly have to find this angle first. Let's just define that angle. We can tell them that angle RPS is equal to, and this should have been done before this. So angle RPS is equal to 180 degrees minus the angles we have here. We have angle X in this triangle and angle Y inside this triangle on the top, like that, okay? So we're going to say 180 degrees minus X plus Y. And so when we say PR over sine Y, okay, so PR over sine Y, we're clearly going to say it's equal to this side, RS, which is Z, over this angle, which is, so over sine of this angle, which is 180 degrees minus X plus Y. Okay, so this is over RS, which is Z. So Z over sine, and it's this angle 180 degrees minus X plus Y. And then they clearly just applied sine's reduction here. Okay, so the goal is still to find PQ. We're just trying to find PR so we can substitute it into this equation. So let's find PR. Let's simplify first. We have PR, and then to get PR on its own, you need to get rid of this sine y. You can multiply both hand sides by sine y. So now it's in the numerator, and we have this is equal to z sine y over, and in the denominator, this, if you use signs reduction, because this is 180 degrees minus a single angle, so this just becomes positive sine of that angle since it is in sine's quadrant. So this just becomes sine, and then this is x plus y. You see where they get the x plus y, okay? And the sine y. And now, because we have PR, we can just substitute it into this equation. So we were saying that PQ is equal to PR times sine W. So PR is all of this. So that is Z sine Y over sine X plus Y, and then multiplied by sine W. And finally, just simplify. I'm just making sure I'm putting it in the same order. Yes, sine Y and then sine W. And so finally, PQ is simply equal to, and it's equal to Z sine Y sine W all over sine X plus Y. And that is our answer. Moving on to the next question. And then the final question says, determine the value of PQ. So determine PQ if Z equals 1000 meters. So we know Z, and W is equal to 90 degrees minus X, and then X is equal to Y. Okay, so, they're giving you everything here. So let's just take this previous equation we had and substitute. Okay, so yeah, because we have 90 degrees minus X and stuff like that, we're probably going to just have some cofunctions. So Z is 1000 meters, 1000 multiplied by, and then we have sine Y. Okay, sine Y, now Y equals X, and W equals 90 degrees minus X. So that means everything here, W, so just these angles, W and Y, they can be written in terms of X. So we can leave everything in terms of X then. So this is sine Y, but since Y is equal to X, you can just call it sine X. I'll just put it in red so I'll remember. So this is sine X multiplied by, and then this is sine W, and W is 90 degrees minus X. So this is sine 90 degrees minus X, also in terms of X, and then all over, and we have sine, okay, yeah, those two angles are the same, so they'll just become 2x. Okay, so x plus x, since y is equal to x, which is 2x. Okay, so just a bit of simplifying. PQ equals, so 1000 and multiplied by sine x. This would simplify to, because it is sine 90 degrees minus x, we can use cofunctions, and it simplifies to cos x. Makes sense, okay, because the denominator is sine 2x, which we can use its identity, which is 2 sine x cos x using double angles. And so PQ is equal to, you see how these would cancel because they're exactly the same. So 1000 divided by 2, which is 500. And we saw that, Z was in meters. So PQ is a length. So it's also in meters. And that is our answer. And that is it for question 5. Question 6. And just note that in question 6, 7, and 8, we need to give reasons for any statements made. Okay. Question 6 says, given triangle ABC with DE parallel to BC as shown in the figure below, we need to prove that AD over DB is equal to AE over EC. Okay, so we need to prove the proportionality theorem. Okay, so to prove the proportionality theorem, we first start off by drawing heights. Okay, so heights for these triangles. So we're looking at this triangle ADE, and we're going to draw a height for it because we need to include AD, right? And AE, of course. Now, one way that we can do that is to make AD a base of this triangle ADE. So in order to use that as a base, we also need a height. The height of this triangle, if this was the base, it will be drawn from the highest point of the triangle down to the base, and it will be perpendicular to that base. And we're going to go ahead and call that height H. And then to include AE, we're also going to use AE as if it's the base of this triangle. And if that was the base of the triangle, then the height of this triangle can be drawn from D all the way to AE, and it will also be perpendicular to AE. And we can go ahead and call that height K. And now, to use DB and EC so that they can also be included in this calculation, we're also going to use them independently as bases. Okay, so if this is the base of a triangle, you can see that we don't have a triangle here. So what we're going to do is form one. And we can form a triangle here using DB as the base. And we'll do that by joining E and B. So now we have this triangle BDE. And then we're going to do the same thing on this side to make EC a base. So we're going to look at EC as if it's a base, and we're going to form a triangle here joining D and C together. Okay, lastly, make sure to write down any constructions that you have made. Okay, there we go. And now to prove this theorem. So we're going to use these sides as the basis of their respective triangles. And in order to do that, let's go ahead and take a look at this triangle on top. But we're looking at this with this being the base of this triangle. So triangle ADE. Since we're using their bases, we're going to use the areas of these triangles, okay, in order to include these dimensions, these bases. So looking at this triangle with the base AD, we're saying that is triangle ADE. And we're going to find the area of triangle ADE. And this is equal to a half multiplied by our base multiplied by our height. But let's go ahead and see what the base is here. We already said the base is AD, and we can see that the perpendicular height that we have is H. So multiply by AD multiplied by this height of H. And now we're going to put this area of triangle ADE, we're going to put it over the area of triangle. Just note how this has been written. It has been written as AD over DB. So we're going to put it over the area of the triangle with DB as a base. So here is our triangle. You see that here's where we have DB as a base, and it is this triangle BDE. So we'll say over the area of triangle BDE, and this is equal to a half multiplied by its base BD multiplied by its height. Now looking at this triangle, do you see that this is an obtuse triangle, okay, with this being an obtuse angle? So with this triangle, what exactly would its height be? Well, if you extended the base and you went all the way to this point, do you see how this height has been drawn from the highest point of the triangle E, which is also the highest point of this triangle BDE, and then down to an extension of the base, and it's perpendicular to that line. So it means that H is also the height of triangle BDE. Okay, so we can put that down. So when we say multiply by the height, we're also saying multiply by H. And there we go. So now when we simplify this, you see that a half and a half are exactly the same. They would simplify to 1. And then H and H also cancel. So this is simply equal to AD over BD. Okay, so we've got this side. Now let's take a look at this side. AE over EC. With AE over EC, if AE was the base of this triangle, we would say to find the area of this triangle, again, we're going to say area of triangle ADE, okay, but AE is the base of the triangle this time. So we're still saying area of triangle ADE over, and remember the whole point of doing that is to get to this point AE over EC. So we're taking AE as the base and then EC as the base of this other triangle that we have here. Okay, so let's just write down what that would be. This would be equal to a half multiplied by its base, which we can see is AE, multiplied by its height. And you can see that if this is the base of the triangle, then the height is from the highest point down and is perpendicular to the base. Okay, so that is K. So multiply by K. Now, the triangle that this goes over is the triangle with EC as a base. And you can see that this is this triangle DEC. So DEC has this base EC. And what is its height? Well, that would also be measured from the highest point of this triangle DEC down to the extension of the base, and it's perpendicular to that. So you can see that that is also the height k. So they are sharing a height, just like these two triangles, the one with the base AD was sharing a height with this one. Okay, so to find that, we would say over, and we're just saying the area of triangle. So that is triangle DEC. So over the area of triangle DEC, which is also equal to, we'll say equal to a half multiplied by its base, which we could see was EC, and then multiplied by its common height, which is also K. And then likewise, these also cancel. So a half and half cancel, K and K cancel, and we're left with AE over EC. Now, just because they simplify to AD over DB and AE over EC doesn't just automatically mean that they are equal. We would still need to find some logical reason for them being equal. So let's take a look at their areas. You see how in this triangle, we use the area of triangle ADE, and here the area of triangle ADE. So that means those are exactly the same because we're using the same triangle. Okay, we just looked at it differently, okay? Looked at the bases as if they were different bases. So we can say that the area of triangle ADE is equal to the area of triangle ADE. It's still exactly the same, okay? Same triangle. But now these two triangles on the bottom, BDE and DEC. Let's look at those triangles. With these two triangles, do you see how if you look at them as if DE is their base, then it means they have the exact same base. This triangle BDE and the triangle CED, they have the same base, okay, if we look at them like that. And how would we measure their height? Well, you would measure their height from the highest point of the triangle, B, okay, and this is also C, the highest point of that triangle, the blue triangle, and you would measure it from that highest point down, okay, and it will be perpendicular to the extension of the base. So if we extended that base, it would be perpendicular to that. Now, do you see how this is exactly the same? If you also have to measure from here to this base, okay, the extension of the base, do you see how these heights are exactly the same? And the reason they are the same is because they lie between parallel lines, okay? So their heights are exactly the same. And so that's what we can state here. So we can state that the area of triangle BDE and the area of triangle DEC are equal. So we'll tell them that the area of triangle BDE is equal to the area of triangle DEC. And they're equal because they have the same base and they're between parallel lines, so they have the same height. Okay, they have the same base DE and they lie between parallel lines, so their heights are also the same. And now because we were able to conclude that they were equal, we can therefore say that this means that the area of triangle ADE over the area of triangle BDE is equal to the area of triangle ADE over the area of triangle DEC. And so it means that whatever they simplify to would also be equal. So that is AD over BD, or I could really have just called that DB since that's how it was written. Okay, so that is AD over DB, and that is equal to AE over EC. And that is how we prove this theorem. And that is it for question 6. Question 7 says, in the diagram below, AC and CE are tangents to the circle with center O. B, D, G, and H are points on the circumference of the circle. HG is produced to F, and then we have BD is equal to BH. Okay, so we have a nice isosceles triangle over here, and they tell us that angle D1 is X, and angle D4 is also X because they are equal. Okay, so the first question is to find 4 other angles equal to X. 4 other angles. Okay, let's see. So we already know we are at a big advantage here because we have this tangent. So, and it's a tangent you see on both sides. So if this is a tangent over here, we can just use the tan chord theorem. Here's the angle between the tangent and the chord. So it's equal to the angle at the circumference subtended by that same chord. So this is X as well. Okay, so we know that is X. And we can go ahead and put that down. We can tell them that angle H1 is equal to x because of the tan chord theorem. Okay, which other angle would be equal to x here? Let's just capture all the, tangent ones. So here we also have an angle between the tangent and a chord. So it's going to be equal to the angle in this circle at the circumference supported by that same chord. So this is also x. Angle H2 is also equal to x. So we can tell them angle H2 is equal to x as well for the same reason. Okay, and then what else do we have? Well, let's just focus on the things that they told us, the special things. We've used the tangents, okay? There's no angle on this side, so we can't really use that tangent. But they did tell us that BD and BH were equal. Since those lines are equal, we have an isosceles triangle here. And then that would mean that the angles opposite their equal sides would be equal. So if this is x, this is also x. So we can see that angle D2 is equal to x because of angles opposite equal sides are equal. So angle D2 equals x, and put our reason. And which other one do we have? Okay, we have an isosceles triangle here, but you see how we have tangents. This is CB and this is CD. So tangents drawn from the same point to the circle are equal. So CB is equal to CD, okay? From that common point to where they touch the circle, they would be equal. So since these are equal, and with this you have to actually state that. You see that? I didn't really need to state that because they already told us that. So start by telling them CB is equal to CD. So CB equals CD. And because that is because of tangents shown from the same point to a circle are equal. And then the conclusion there with the angles would mean that the angles opposite their equal sides would be equal. So this is also x because that is x. Okay, angles opposite their equal sides. So angle B3 is also equal to x. Angle B3 is equal to x because of angles opposite equal sides are equal. And there we go. Okay, those are 4 angles equal to x. We have made sure to also put those down. I'll leave these lines here just in case we need them. Let's just leave them all in the same color so we know, everything that related to x. And that is our answer. Moving on to the next question. And then question 7.2 says, hence or otherwise, prove that BD is parallel to HG. So HG and BD, let's see those. Okay, so this is BD, this is HG. Why are they parallel? Well, if we can think about theorems that refer to parallel lines. If we can find that any of those theorems are true, then these lines are parallel. So we can work with fun angles here. And straight away, I see that if we join DH, we have formed alternate angles. Okay, this is a Z. So you see how this angle is already equal to this angle? They're both equal to x. So we can go ahead and tell them that we can see alternate angles here. Since they are equal, the lines are parallel. So we can tell them D2 equals H2. So angle D2 is equal to angle H2, and they're both equal to x. Therefore, BD is indeed parallel to HG. And this is because the alternate angles are equal. Therefore, the lines are parallel. So I'm also just going to put down, parallel just to show that these lines are parallel as well. Okay, moving on to the next question. Question 7.3 says, show that angle G2 is equal to 180 degrees minus 2x. So this is angle G2. Why would this be equal to 180 degrees minus 2x? Well, they use 180 degrees, so clearly they are making it refer to this straight line. Angles on a straight line add up to 180 degrees. So it's probably that angle G1 is equal to 2x. So then to find G2, you said 180 degrees minus 2x would give you angle G2. Okay, so why would this possibly be equal to 2x? Okay, so I'm looking at this, and after looking at this, I just realized that I can't really see angle G1 immediately being equal to 2x. But I do see this, okay, because I was looking for an exterior angle in this triangle, and, this is already an interior angle. So, yeah, this can't be the exterior angle including this. But if you look at it like this, so just go ahead and look at this shape, right? You see that we have a cyclic chord here. And then this is the exterior angle. Angle G2 is the exterior angle. If this is the exterior angle of the cyclic chord, it is equal to the opposite interior angle. So it has something to do with angle B2. If you find angle B2, then you'll know what G2 is. And this is the one that is 180 degrees minus 2x. So our goal is to find angle B2. Okay, so it's a usual story with Euclid and how you like jump from one thing to another thing. To find this, you must find this, and so on. So how do we find angle B2? Well, angle B2 can be found if we know what B1 is. How do we find B1? Angle B1 is between a tangent and a chord. So it's equal to the angle at the circumference supported by the same chord BH, okay? Subtended by the same chord. So that would be angle D2. So that is equal to x. So that's where we start. We'll tell them that angle B1 first. Angle B1 is equal to x because of the tan chord theorem. And then from angle B1, we can find angle B2. So angle B2 will be found by saying this is a straight line. So the angles on the straight line add up to 180 degrees. So angle B2 will be found by saying 180 degrees minus that x minus the x, the other x that we have, those two x's there. And then this is angles on a straight line, the sum of angles on a straight line. Okay, so angle B2 is equal to 180 degrees minus 2x. And then finally, to find this angle G2, you see that angle G2 and angle B2, okay, they're equal because this is the exterior angle of the cyclic chord, so it's equal to the opposite interior angle. So finally, angle G2 is equal to angle B2. Therefore, it's equal to 180 degrees minus 2x because of the exterior angle of a cyclic chord. Okay, and there we go. We've proven that. Now, this took 3 steps. This was for 2 marks, so there was probably a quicker method. And let me see, what would have been the quicker alternative? Okay, so here is the alternative method that we could have used. You see how this is a tangent and this is a chord. And so the angle between the tangent and the chord D1 and D2, okay, which make up 2x, they would be equal to the angle at the circumference subtended by that same chord. So this would also be 2x. Therefore, angles on a straight line add up to 180 degrees, and this would still be 180 degrees minus 2x. Okay, so yeah, 2 ways that you could have done that. That would have been quicker. But there we go. That is our answer. And that is the last question for question 7. And that is it for question 7. Question 8, 8.1 says, AB lies on circle with center O. Okay, so that's this circle over here. Okay, this smaller circle. And is produced to, so AB is produced to C, okay, which lies on the circle with center P, the larger circle. Similarly, FE is produced to D, okay. BE is parallel to CD. And they want us to prove that ACDF is a cyclic quadrilateral. So ACDF. Let's highlight that. Okay, now with this diagram, it looks simple. And there's an advantage and disadvantage to when it looks simple. When it looks simple, there's not much to distract you. But also when it looks simple, it looks like it doesn't have much information. So really just think carefully about this. Straight away, I see that in order to prove that this is a cyclic chord, remember that there are 3 ways, right? There are 3 theorems that you can use to prove that a shape is a cyclic chord. Number 1, if the exterior angle of this chord is equal to the opposite interior angle, this is a cyclic chord. Number 2, if the opposite angles in this chord add up to 180 degrees, then this is a cyclic chord. And then the third way, if the angles in the same segment are equal, it's a cyclic chord. Now, looking at this and looking at this diagram, you can see that we don't have lines going across. We don't even have an exterior angle in this shape. So I'm going to eliminate these 2 methods, and I'm actually going to focus on this method, which is rare. I barely ever with all these past exam papers I've seen, I've barely ever had to use this method. So this is a new one, and let's just see how we can do this. But I'm sure that they have done this before though. But then again, it could also be new. Okay, let's see. How can we actually do this? Remember guys, never try to start finding random things and then just hope that you get to the answer. Okay, because then that is really guessing. You could go wrong or you could just not find anything. Sometimes it is helpful though, so that you can at least score marks if you did point out certain things that would be useful. So yes, in the case of an exam, you can do that. That would be helpful. But when practicing, don't find random things. You end up just confusing yourself. You need to create a strategy to get to the answer. So we know that we can use this method, right? Proving that the opposite angles add up to 180 degrees. So let's see how we can do this here. Okay, so let's plan this out and just think about which angles we're working with. So we know we need to take two opposite angles, but which ones? Now, I was thinking about going with A just because it's A, first letter. I just thought that maybe they just made a hint, and sometimes they do that, okay? They'll just make the angle that you need to find A, or really it will go in alphabetical order. But we're going to have to think about it. So my first guess, let me just try these two first. Let's go with angles that are between these parallel lines. If we are focusing on the opposite angles in the cyclic quad adding up to 180 degrees, just because of the way the shape looks, then we can focus on angle A plus angle D adding up to 180 degrees. So that's what we're required to prove. Okay, so I'm going to put that down. What we are required to prove, RTP, so required to prove, is we're required to show that angle A plus angle D adds up to 180 degrees. And if we can show them that, then it means that the shape is a cyclic quad because the opposite angles add up to 180 degrees. Okay, so how can we do this? We're going to have to move from one point to another point. So I'm still leaving angle D selected, but just in a less vibrant color so we can focus on angle A. When we are by angle A, where can we move to? From angle A, just because of how simple this diagram is, the other place that we can move to is here. Do you see that in this cyclic quad, in the smaller circle, right? A, B, E, and F, we have a quad there. And this quad has an exterior angle, E2. So angle E2 is equal to angle A. Okay, so we've just moved. We have moved from angle A, and we are now at angle E2. And then from this point, how can we eventually get to here? Okay, so you see how, and now we can use these parallel lines, okay, because we need to form that 180 degrees. Do you see how these lie between parallel lines? And so they form co-interior angles. Okay, so this is co-interior angles, and co-interior angles add up to 180 degrees. And there we go. And so that's how we would do that. So we'll start at angle A, and we can say angle A is equal to angle E2. And the reason for this is because that is the exterior angle of a cyclic quad. It's equal to the opposite interior angle. Okay, so that's done. And now we've moved to angle E2. And from angle E2, you see that because it lies between parallel lines, the co-interior angles add up to 180 degrees. So angle E2 plus angle D that we have there is equal to 180 degrees. And this is because of co-interior angles, okay, on parallel lines. Okay, so you can just specify the lines that are parallel. BE is parallel to CD. So BE parallel to CD. And now this is everything we need. You see, because angle A is equal to angle E2 and these add up to 180 degrees, remember, angle A is equal to angle E2. So in place of angle E2, we can just replace that with angle A. So that means angle A plus angle D add up to 180 degrees. Okay, you can easily see this with this information. We found that these two are equal. We found that these two add up to 180 degrees. So in place of E2, because these are equal, just replace it with A. That means that angle A plus angle D is equal to 180 degrees. And there we go. Okay, we have proven what we were required to prove. So that will prove that ACDF is a cyclic quadrilateral. Okay, because we have the opposite angles in a cyclic quad add up to 180 degrees. And there we go. We can just tell them that. Opposite angles in the cyclic quad, they add up to 180 degrees. Or we can just call it the converse of the opposite angles in a cyclic quad. Okay, so just call it the converse theorem. So converse of opposite angles in a cyclic quad. And that is how we prove that. Moving on to the next question. Question 8.2 says, in the diagram below, AB is the diameter of a circle with P as the center. Okay, and then EP is perpendicular to AB. So this is 90 degrees and this is 90 degrees. And then they tell us that prove that triangle BPE is similar to BDA. Let's highlight those triangles. BPE is this triangle over here. And then BDA is BDA. And I'll highlight that. Okay, so you see that we have one angle down. Okay, angle B1 is a shared angle in both triangles. So that's down. All we have to do is find one more angle in both triangles that are equal. And then we're done. Okay, so 90 degrees is a very good one to go for. And the reason why is because if it's 90 degrees, it's going to be clear to see that, yeah, that angle is 90 degrees. Okay, so straight away, do you see that AB is a diameter? Therefore, the diameter supports a 90-degree angle at the circumference, angle in a semicircle. And that would be it. Okay, so let's just go ahead and write it down. We'll say in triangle BPE, okay, because remember, if you have two triangles and two angles in both triangles are already equal, then by default, the third one is equal. Okay, so I was really only focusing on finding two angles equal, and then I knew I'm done after that. Then that's fine. Okay, so we have angle B1 being common. So angle B1 is equal to angle B1, and this is a shared angle. You can say shared angle or common angle. And then what else is equal? We have these two. So angle P2 is already 90 degrees because they told us those two lines were perpendicular. And we can see that angle D is also 90 degrees. So let's start by telling them that angle P2 was equal to 90 degrees because this was given. Okay, we were initially given that EP is perpendicular to AB. So EP was perpendicular to AB. And then we can also say that we can see angle D is equal to 90 degrees as well. Angle D is equal to 90 degrees, and that is because of angle in a semicircle. Okay, and so this is one angle that is equal. We can finally conclude that angle P2 is equal to angle D. So these are two angles we have, this angle and this angle. And then the third angle in each triangle will be equal by default. So this angle, angle A1 plus A2, which we can just call angle, we can call it angle A because it's really just on its own like that. So angle A is equal to the angle here, the third angle here, which is angle E3. Okay, so there we go. We can say angle E3 equals angle A because it's the third angle in this triangle, or you can say the sum of angles in a triangle. Okay, so now that we have these three equal, we can finally just conclude that these two triangles are similar. So finally, triangle BPE is similar to triangle BDA because we have three sets of equal angles. And that is our answer. Moving on to the next question. Question 8.2.2 says, hence prove that BE is equal to PE squared multiplied by BA times BD over BP. Okay, so with these questions, once they ask you to prove that, two triangles are similar, and then they ask you a question like this, it usually has to do with the two triangles that are similar. So I'm going to take this and I'm going to just find the dimensions that they used quickly. Okay, so looking at this, you see how we have PE. Okay, let's start with BE because BE is over here. BE came from the first letter and the second letter. So that side BE. And so BE would go over BA BA. Okay, we have to take it over BA. So first and second in the second triangle as well. So BA. BP, and then I'll just compare it with what we have here. And we have PE. Okay, so where's PE? We have PE, and then I have to take PE with DA. So PE over DA. Okay, so that's usually the case, but let's just see what we have here. There's 1, 2, 3, 4, 5. 5 lengths that they're referring to. We've got PE, but it's PE squared, so there's probably another PE. We have BE, we have BA, and we have BD. So where did PB and the other PE come from? Well, really BP. Okay, before jumping to the conclusion that they used another triangle, let's actually just see though. Okay, do we see a triangle with PE and then BP? Okay, that could be similar to one of these triangles. PE and BP. PE and BP. Well, the only other triangle that would go with that, right, would be this triangle. Okay, this blue triangle over this triangle, this little triangle over here. So if we highlighted that, this is the triangle I'm referring to. That's the only one, because you see that if this is the center of the circle, then BP is a radius and then PA is also a radius. So they could have used that triangle as well. Okay, let's just roughly check because I can't just ignore things. I honestly feel like it's actually using these two triangles twice and it's using PE twice, but I still can't just ignore this. So let me see. If we were saying these two triangles are similar, which we can see they are, you see they both have a right angle triangle. They are both created using this hypotenuse, EB. So we can see that first, they are definitely similar because they're congruent. Here's why I say they're congruent. You see how they have 90 degrees and then 90 degrees. They are sharing this side PE, and AP is a radius and BP is also a radius. So that's side angle side. So they're congruent. Naturally, their angles will also be equal. Okay, congruency just means that the triangles are exactly the same in the lengths of their sides and their angles. Okay, so naturally, if two triangles are congruent, they're automatically similar as well. Okay, so these two triangles are similar. Let's just put them down quick. So if we have B, P, E, this triangle, and triangle A, P, E. Yeah, I don't think this is a good idea because no matter how I name these triangles, trying to include PE, seeing that it's one of the missing sides here, and then we have BP, I see that if I had to do that, let's try this, right? If I said BP over, I have to take it over AP because I took the first and second, so first and second here. And then it's equal to, you see how this just ends up giving you PE over PE? That's a problem. I can't really work with that. Yeah, PE is on the denominator, but not in the numerator. And how will we actually get rid of that eventually? Okay, so here it is. So even if eventually we found a way to work with these two equations, there's still going to be a problem because of that PE. Even if I did it in a way where I tried to make P the subject here and then P the subject here, I can still see how that will be a problem because in the equations, it will include DA and there will still be only one PE. So it's clearly not that triangle. Let's not work with that. Okay, I'm going to just go with this. So I'm going to ignore that and let's just go with this that we were referring to at first. Okay, I think they used two triangles here. Okay, they just used the proportions twice. So we can take it like this. And then let's also just see if we included the third sides in these triangles. So we took the first and third, second, and okay, so first and second. So that would be BP over BD. Okay, so over BD. And let's see how that would work. Now, before just working on it, I'm going to compare it to what we have here and just see the sides that we have available. So we have BE, great, okay. We have PE, we have two PEs really. We can find two PEs, okay, because I'm just putting them all together. But then we also have BA. So we've got, let me just mark it here. We've got BE, we've got BA, we've got BD, and we have BP. And then, of course, we have PE, which we can use twice because we can just use this, okay, ratio twice. So the only thing that would be, out of place is dA. But that will not be a problem if we use this twice. So here's what I mean by using it twice. You see, this is not a proper equation. You're saying something is equal to another thing, which is equal to another thing. Okay, that's not how equations work. Equations, it's one thing is equal to another thing. So here is how we can form these two equations. We can take BE, right, this one with BE, with this equation, with this ratio with PE. So we can take this as BE over BA and say this is equal to PE over DA. And then our second, and of course we'll have to put a reason here. So I will say similar triangles. You can name the triangles if you want to. Then the second equation that we're going to get, we can pair these two together. That way, PE is represented twice, and then we have DA, which we can just make the subject of each equation. Okay, so here's the thing. We can also just say this is BP over BD is equal to, and then we have again PE over DA. Okay, so two equations, again, because of similar triangles. So this part you can put in pencil. You can also leave it there. It's not a problem. There's nothing wrong with leaving it there, but this is what we're working with. And now with these two equations that we have, I'm just going to cross multiply. And my goal is to make DA the subject because I see that DA is not even included here. So if I can make DA the subject, eventually I can say DA is equal to DA. And because everything else is included, it should work out. So, okay, let's go ahead and do that. So this is BE multiplied by DA. Okay, so it's times DA and then is equal to, and then that is BA multiplied by PE. I can't see how this is not going to work out, to be honest, because the problem is PE is in the numerator in both equations. Okay, I'm just going to continue. Let's see. So, and the other equation that we have is BP multiplied by DA. I'm going to make DA the subject in both. Is equal to, and we have BD, so we're cross multiplying. Okay, multiplied by PE. And then in both equations, DA can simply just be made the subject. So to leave DA alone, you're going to rewrite this as BA times PE over BE. And then this one would simplify to DA equals BD times PE over BP. And then naturally, because DA and DA are the same thing, we could equate them. And you see, this is why I'm saying I don't think this is going to work out. So BA times PE and then over BE is equal to, so you have to tell them DA equals DA first, and then we're equating them. So this is equal to BD multiplied by PE over BP. And then the whole point of this will be to make BE the subject because that's what we had. We had BE is equal to and then everything else there. Okay, so if you did that, two ways you can do it. You can decide to do it the long way, cross multiplying, which I think I should just show the step-by-step method. So let's say we had BE multiplied by BD, right? So we're cross multiplying and then multiply by PE. I would say it's equal to, and then I will multiply like this and be BP multiplied by BA multiplied by PE. And then we could just make BE the subject. So if you make that the subject, then the equation we end up with is BE equals BP times BA times PE over BD times PE. See how this doesn't work out? And the reason I've spotted that it's not going to work out already from here, because PE is in the numerator. We also tried using this triangle here, the only one that seems similar to that, and it doesn't work out. And I don't even want to try using this. I don't even want to try and find out because now it's just going to include new sides that we don't even need. Okay, like AE and DE. So with this one, I am not sure because it was working out well when we plan it out and we see the triangles that they're clearly using. All these sides are there. They really are there, but they may be something wrong. So what I'm going to do is, this is a 2022 paper. So let me go ahead and check the memo and see what they did there. Okay, I found the problem. Okay, so here's the problem. The method is fine, and it's even the same method they used. I couldn't really find any other method. Like, couldn't see any other triangle that was involved. It was those two triangles. But here's the problem. You see how they follow this as well? They also say, yes, BP over BD. They take the lengths of these that we have, okay? Like we did, we compared all the lengths. But the problem was, they spotted DA, that was good. And then they made DA the subject in one equation and in the second equation. The problem was this first equation. In this first equation, let's look at it from here, okay? Because up until here, this is still true. If you say BP over BD, it is equal to PE over DA, then that is correct. But then once you decide to make DA the subject here, you see how this equation is not going to make any sense now. If you had to cross multiply, you get BP times DA is equal to BD times PE. And then if you make DA the subject, you see that for this to be left alone, you have to divide both hand sides of the equation by BP, and that's all. And so this equation should have been BD times PE over BP. And then that would have been the equation of DA, because they follow the same steps here. They said PE over DA equals BE over BA. And then you see how they make DA the subject by leaving DA. So it's kind of like taking DA to this side. And so you see that BE has to go there. So what stays here on top would be PE, correct? What goes on the bottom is BE. And what will go to the top, because we're bringing this over to this side and we're making it a subject, we moved BE to the side, so it went to the denominator. So the only thing that would come up here would be this BA. Okay, you could also cross multiply, make DA the subject. It would be BA that you have here. So you see how they follow that? And that's perfect. But because they didn't follow it here, then, So that's where it seems like the error came. So there's an error in equation 1. Because you see, for you to be able to say this is kind of like saying x is equal to a over b, right? On one hand, I said x is equal to a over b, like dA equals this over this. And then all of a sudden, I decide to swap the numerator and denominator and say x is equal to b over a. That doesn't make sense, okay? Okay, just like 2 over 1 is not the same thing as 1 over 2. So that was where the error came in. And so that's why it was so complicated to actually get to the answer, because the answer had an error in it. Okay, so you guys can still use it to study. Had, those two equations worked out, then yes, we would have gotten that. So the only thing that it would actually simplify to would be, PE and PE would cancel because they're exactly the same. So at the end of the day, BE would simply just be equal to BP times BA over BD, and that would be the equation for BE. Okay, so that was the last question, and this is worth 12 marks, question 8, and that is it for question 8. So that is it for this paper. If you guys have any comments, please leave them down in the comment section. If you enjoy this video, please like it. It really helps with the growth of the channel, and I will see you guys in the future videos.